Hi everybody. We are here today to go over the LabFlow experiment for constant pressure calorimetry. Um, Thermodynamics and thermochemistry are one of the things that really challenge students as we go through general chemistry. I think mostly because of the sort of detail that's required to go through the math. So this lab is a good example of three different types of calorimetry that we might do in the lab. It goes through enthalpy of neutralization. So you may know from experience that when you mix together an acid and a base, of course, they neutralize one another to form water and a salt, and there is a significant amount of heat released from that. The solution feels warm. And if the acid and base are strong enough, you can actually heat that solution as it's being mixed to cause a safety concern. So sort of a good thing to be aware of there. The second one here is the enthalpy associated with dissolving a compound. So when salts dissolve in water, if they absorb energy, that would feel cold to us, an endothermic reaction. Those are useful in things like instant cold packs you might find in a first aid kit. If they release energy, an exothermic reaction, as they dissolve, then that would feel warm. So again, the idea of a first aid or a sort of maybe a hiking hand warmer or something like that. And the third part is a specific heat of a metal. So you may remember that all materials have a particular constant, an intrinsic property that has to do with how their temperature changes as they absorb or release energy. Metals are no different. So we will measure the specific heat of a metal by immersing a hot piece of metal into a cool container of water, measuring the resulting temperature change of both the metal and the water, and then doing some math to calculate how that metal behaved. So as you go through the lab, of course, I hope you read the PDF first. There's a nice introduction here to all of these equations. Most importantly, and I'll come back to this a couple of times as we go through, Q of the reaction versus Q of the calorimeter. Q is our variable that we use for heat energy. So it typically has units of joules or calories, or 1,000 times bigger, kilojoules or kilocalories. Both of those are common. This lab uses calories, so we're going to stick with that today, but both are common. But what I want to point out here is the sign. You have to think about the reaction that's occurring, whether that reaction is neutralization or dissolution in these first two parts. You have to think of that reaction as occurring within the calorimeter. So if the reaction releases heat, the calorimeter would be absorbing heat. It's the same number, but opposite in sign, because the energy is flowing from one place to the other. Signs mess people up when they go through thermochemistry and thermodynamics calculations, especially early on. So I'm going to point out signs as we go through here several times. As we go on further, we find some pretty important reactions. This one, Ca4 here, is probably the most important, that Q equals mc delta T. And you'll see that in lots of different ways, but we'll look at this as we go forward. M is always mass here. C is our specific heat. So the units there will be energy per mass per degree Celsius. And T, or delta T here, is our change in temperature. Deltas, changes in chemistry, are always final state minus initial state. So if something's getting hotter, that delta T would be positive. If something's getting cooler, it would be a negative. All right. As we go down a little bit further here, this spells out each part, and I'm going to refer back to this here and there, but the equations that I'll be using are all spelled out through these sections. Okay. I have gone into the lab and pre-filled, pardon the quick scrolling, pre-filled the data that was given to me in my virtual collection of data, just to save us a little time and a little poor penmanship. So this is what I got for heat of neutralization. Now you're going to be asked to do a few things here. First, calculations for number of calories evolved. Now, if we go back up to the top and we look at those equations, remember that number of calories or heat is Q, and that is always going to be mass times the specific heat times the change in temperature. Now, of what? Well, the calorimeter, because that's what we were measuring the temperature of. So the calorimeter is full of liquid. In this case, the liquid, the mass of that calorimeter is going to be both of these liquids together. And so when we add those up, that's 100.1 milliliters. And we're making the gross assumption here that these have a density of 1 gram per milliliter, which at the concentrations employed in this lab, that's a fair assumption. So we're going to say here that the mass we're dealing with is 100.1 grams. Okay. C, well, these are nominally water-based solutions, and so we're going to use the specific heat of water, which again, your textbook and reference sources will have two values for this. Since we're dealing with calories, we're going to use the calorie value, which is 1 calorie per gram per degree Celsius. And then temperature change. Well, here, final minus initial, 31.2 minus 26.1, and we end up with a temperature change of increasing 5.1 degrees. Okay, so that's what we'll put in here, 5.1 degrees C. Okay, now when we do the math on this, I'm going to pull my calculator up here for a second. When we do the math on this, we're going to say 100.1 times 1, of course doesn't matter, times 5.1. We get 510.51. I'm not going to round this in my intermediate calculations because I'm not done yet, but my unit is calories. Now notice here, this is a positive, okay? So the calorimeter absorbed energy from the reaction. Okay, the calorimeter is going to get hotter. The reaction was giving away energy. So when we get to that, Q of the reaction will be the opposite of this number. Okay. Now, up in the procedure up there, it tells us that, move my calculator out of the way, moles, down here, calculations for calories evolved per mole. Well, we need to know how many moles of hydrogen were evolved, or neutralized, I guess, here. So, well, how do we do that? Well, we look at this and we say, how much hydrogen did I have? How much H plus? Well, so I started out with 49.9 milliliters of that stuff, HCl, which I have to convert with my handy 1,000 milliliters per liter. And now to get to moles, I need the concentration. Well, when we read the manual, they used a really convenient for us 1.00 molar solution. That's 1 mole, 1.00 moles per liter. Okay, and since HCl is a monoprotic acid, I'm going to get 1 mole for every mole of the molecule here. So I can go ahead and do that math now. 49.9 divided 1,000 times 1. Okay, 0.0499 moles of H plus. Now, if we had been using a diprotic acid, for instance, if this were sulfuric acid, H2SO4, we would want to double this number. Okay. Now, lastly, let's move him over there for a minute and make him a little smaller. All right, lastly, calories evolved per mole. Well, listen to what that's telling us. So we want delta H of neutralization. So delta H is always just Q normalized by something. So here's Q of the reaction. All right. Q of the reaction is the opposite of what we had up above. Right? If the calorimeter absorbed 500 calories of energy, it must have released that out of the reaction. So negative 51051 moles was 0.0499 moles of H plus. And when we do the math on that over here, all right, 510.51, flip that to negative, divide by 0.0499, I get negative, come on pen, there we go, negative 10.230.66. My units here, calories per mole of hydrogen. Okay, now this is the number you would round to significant figures, right? So my volumes up here had 3 significant figures. I'd round this to 3 significant figures, 10.2 kilocalories per mole, negative. Now, in case you're wondering, if you go to a reference source like the CRC handbook and you look up the heat of neutralization of HCl with NaOH, you're going to get about 13.7 kilocalories per mole. We got 10.2, so not bad. Experimental data, notwithstanding, we're in the right ballpark. So that's how you're going to do this. Q equals MC delta T for the calorimeter gets you your energy change. The starting material here, we wanted moles of H plus, so starting material here is going to tell us how much stuff got reacted, and then we divide those two to get our delta H. Okay. We're going to use a similar method as we go into part B. Now, part B is dissolution of salts. Now, you'll see I didn't put in my magnesium numbers over here because I wasn't going to do this twice. It's just an example, right? But what I want you to notice here is that for ammonium nitrate, our temperature change here goes from 23 degrees down to 19. Right, so that's a negative temperature change, negative 4.1 degrees C. And that's because this is an endothermic reaction. All right, this might be in those cold packs. That's reducing the temperature. It's going to feel cold. Magnesium sulfate, although I didn't put the numbers here, magnesium sulfate dissolution is exothermic. And so you're going to get a positive delta T. But otherwise, the mechanics of what we're going to do here are the same. All right, so what we're going to do here is we're going to see when you look up in the instructions that delta H of dissolution is going to be Q of that reaction, the dissolution reaction, divided by moles of the salt that you dissolved. Okay, so a very similar kind of idea to neutralization. Q is the raw amount of energy. Delta H is that normalized for how much stuff actually reacted. Okay, so we're going to approach this in the same way. How do we find Q? Well, we can't find Q of the reaction because we can't stick a thermometer into the atoms. But what we can do is find Q of the calorimeter. Again, MC delta T. Okay, mass of the calorimeter here now is both of these things together. Again, we're going to assume that the water is 1 gram per milliliter. It's pretty safe at these temperatures. 50.5 grams of water plus 1.917 grams of salt gives me a total mass in my calorimeter of 52,417 grams. Okay, that's the number I'm going to use here. 52,417 grams. All right, again, it's nominally a water solution, so we're going to use the specific heat of water, 1 calorie per gram degree Celsius, and the temperature change now of that water is a negative 4.1 C. I circle my negative signs so I don't lose them, okay? It's just something I picked up over the years. So Q of the calorimeter now is the result here. 52 grams times that 1 specific heat times 4.1 negative gives me negative 214 0.9097 units are calories. Okay, so Q of the reaction, we might as well just write it right here. Q of the reaction is the opposite of that. Same number, 214.9097, but positive. All right, that's the number we're going to want to use up here. How do I find moles of the salt? Well, you should by now in Gen Chem know how to do grams to moles conversion, right? I put a little line here. I started with 1.917 grams of ammonium nitrate. I'm going to use my handy dandy periodic table to figure out how many grams per mole that is. So if I go and I add up my nitrogens and hydrogens and oxygens and stuff, I'm going to get that has a formula mass of 80.04 grams per mole. And when I divide those, 0.917 divided by 80.04, right, I'm going to get an itty bitty number of moles. 0, oops, okay, fine, sorry about that. 2, 3, 9, let's say 5, 1, okay? Remember, modern calculators give you just a bajillion numbers, decimal points. We don't need all of those, of course. So since I know I'm going to round ultimately to, 3 or 4 significant figures, if I'm keeping 5 here, that should be just fine. Could have kept another one if you wanted to. All right, now we're going to go get our big equation. Delta H of dissolution. That's Q of the reaction. So 214.9097 calories divide moles of salt that reacted, 0.23951 moles. And when I divide those guys, 214.9097 divided by 0.023951. Do not lose that leading zero, everybody, okay? It's real easy to lose leading zeros. Don't do it. I come out with a number here of 8972 and some change calories per mole of salt. All right. And this is a positive number, meaning that the reaction is absorbing that much energy. If the reaction's absorbing energy, the surroundings, the calorimeter here would get cold because it's losing that energy. And so it's endothermic. It's what we'd expect. The literature value on this one, if you go look it up, it comes out to about 6,100. So again, within the bounds of experimental data, I'd hope if I actually collected this data, it would look a little better, but I'm using the stuff that LabFlow gave me. So I'm in the right ballpark. That's good enough for me. Now, part C of this thing is the one that I think maybe makes the most intuitive sense. Okay. So specific heat of a metal. I'm going to go up here a little bit so I can sketch this real quick. All right, so what I'm doing is I'm taking a super hot piece of metal, all right, and I'm taking a container of cool water, and I'm putting those two things together to get, good thing this is not an art class, right? Some sort of warm-ish mixture, okay? Now what's going to happen? Of course, the metal's going to cool down. In this case, 95, oops, what did I do over there? Don't like that, get rid of that. 95.2 degrees was the data I was given here, down to 27.1 degrees. Okay, the water is going to get hotter. So it started at 23.5 degrees in my data, and it got hotter. This is what people have been doing forever. This is what the radiator in your car does. It takes energy out of circulating basically water and heats up the metal, and then the air rushing past the radiator as you drive cools down that metal. This is what blacksmiths do, when they forge a knife or something out of, molten hot steel. They cool it down in liquid. That liquid doesn't immediately boil because water has a ridiculously high heat capacity compared to metals. Our job is to figure out what the specific heat is of this metal, and we could use it to identify the metal, although the way this one is set up, we were given the identity of the metal here. But this is a common kind of a question. You did this experiment, what metal is it? And then you'd look in your textbook or you'd look in the assignment or something and you'd look at a list of metals and you'd say, okay, it could be copper based on these particular things, or it could be zinc, or it could be whatever. So the concept here that we have to remember is that energy isn't being destroyed or created, right? The energy of the metal is going to be equal to the energy of the water, but opposite in magnitude. Okay, and it doesn't matter which side you put this negative on, but the point is the two numbers are the same, they just have an opposite sign. Here, the metal is releasing energy, it's getting colder, it's going to end up with a negative Q, and the water is getting a little hotter, it's going to have a positive Q value. The point is they're opposite to one another. For both of these, we can say Q equals M for the metal, C for the metal, delta T for the metal. All right, big old negative sign out front so we don't lose it. Q of the water is M of the water times C of the water times delta T of the water. All right, you know 5 out of these 6 variables. We're solving for a specific heat of the metal, but we know the mass of that metal, we know its temperature change, or we can easily calculate it. We know the mass of the water, we know its specific heat, and we know the temperature of that water, the temperature change. Now, I like algebra, so I would rearrange it to say the thing I care about is all this other junk. M of the water, C of the water, delta T of the water, big old divide sign, M of the metal, and delta T of the metal, right? If you're not, get comfortable with it. But otherwise, you could just plug in the 5 numbers that we know here, okay? I'm going to scroll a little. Now, let's start plugging it in, all right? C of the metal is big old negative sign. Mass of the metal was given to me, 20.401 grams. Okay. Specific heat of, oh, sorry, scratch that. Don't get messed up here, right? See, this is how people get messed up. That's why I put all those little subscripts on there. This is mass of the water, right? So again, assuming 1 gram per mil for density. So 50.8 mils is 50.8 grams of water. Gosh, that would have been embarrassing. All right. See, now I can pretend like I did that on purpose. We use the specific heat of water. We use the temperature change of water, right? So the water went from 23 up to 27. So when we subtract that, we get a positive 3.6 degrees. Okay. Big old divide sign. Now, here's that number I wanted. Mass of the metal was given to me. This is my 20 number in my data table up there. Okay. Temperature change for the metal. Well, now the metal went down in temperature, ended at the same place, right? But it went down in temperature. When you subtract those two, you get negative, oops, stop that, negative 68.1. Okay, 68.1, yes. All right, so when you do the math on this, all right, where's my calculator? Bring him up here. Okay, I'm going to make a quick note here that my two negative signs are going to end up canceling each other right here and right here, so I'm just not going to type them in. 50.8 times 1 times 3.6 across the top, divided by 20.401 on the bottom, and divided by 68.1. That gives me this number of 0.1316. What are my units? Calories per gram degree Celsius. I know those units because it's a specific heat, but also because my grams canceled here, my degrees canceled here, and so what I'm left with is this compound unit here. So 0.1316 calories per gram degree Celsius. Well, all right, how do I know if this is correct or not? Well, again, if I go to a reference source and I look up the typical specific heat for steel, that's what I was given in my example here, I find that the literature says it's 0.115 calories per gram per degree. So 0.115, 0.131, again, I'm in the same ballpark. So I am happy enough with that. All right, so that is how we're going to do this thing. Pay attention to your signs in particular, okay? Remember that there's always the system that you're looking at and the surroundings, and we're typically measuring the surroundings because that's where we're doing it. That's where the thermometer in these cases is immersed. Our surroundings for all of these is the calorimeter. The system or the reaction, the thing that we're measuring, is sometimes easy to figure out. It's relatively easy to see how this chunk of metal would release heat, out into the surroundings as that water absorbs it. That's relatively easy to understand. The one where we're talking about a chemical reaction or a dissolving salt being that system, that thing, it's the same idea, right? So don't get twisted up about it. In most of these examples, in the textbook, in the homework, everything like that, you're going to be measuring the calorimeter. You're measuring the surroundings. And so just recall that the system, the reaction, the dissolving salt, the chunk of metal, has the opposite value. All right. So with that, I am going to shut down this video. Thanks for listening. As always, email me if you run into any trouble, and keep up the great work. Take care, everyone.